Active Noise Cancellation technology commands a valuation exceeding $13 billion. These devices provide an immediate acoustic sanctuary in chaotic transit and open office environments, but they carry a highly disruptive paradoxical side effect: the onset of profound biological distress in a significant demographic of users. For the estimated 1.1 billion young people worldwide at risk of noise-induced hearing loss, this technology is a vital intervention. By stripping away environmental interference, it allows users to consume media at significantly lower, safer decibel levels. Yet, alongside this widespread adoption, audiology clinics report a highly specific clinical pathology. Upon activating the noise-canceling feature, users experience the rapid onset of severe headaches, intense oral pressure, dizziness, and mild nausea. Consumer forums often debate whether these headaches are psychosomatic or signs of direct acoustic trauma to the eardrum. However, clinical evidence points to a multi-vector physiological response arising from the collision of neurovestibular integration and acoustic physics. It is a complex physiological rejection of synthetic silence. To understand why fabricating an acoustic void triggers intense physical pain, we must systematically deconstruct the physical laws of sound, the brain's neurovestibular sensory networks, and the rigid biomechanical constraints of modern hardware. Active noise cancellation does not establish a physical barrier against acoustic energy. It operates on the principle of destructive interference, deploying an electronic countermeasure to continuously neutralize incoming mechanical pressure. This diagram illustrates the mechanism. Micromicrophones detect incoming ambient sine waves. Instantly, an onboard digital signal processor calculates and broadcasts an exact mirror image anti-noise wave, 180 degrees out of phase. Superposition sums the pressure to zero. This works effectively for low-frequency continuous sounds. A 100 Hz sound wave stretches roughly 3.4 meters in length. These elongated waves grant the digital processor ample computational time to generate a perfectly aligned antiphase response. However, above the 1 kHz threshold, sound wavelengths compress to mere centimeters, making them highly transient. At these frequencies, processing latency causes the waves to misalign. Instead of canceling out, the peaks align, causing accidental constructive interference that physically amplifies the incoming noise. To prevent this amplification, manufacturers program algorithms to deliberately taper off active cancellation capabilities for high frequencies. The continuous rapid-fire sampling required by the processor leaves behind a distinct high-frequency quantization noise, perceived by the user as a faint digital hiss. The user is left listening to perfect low-frequency silence paired with residual high-frequency noise and persistent electronic hiss. It is a highly skewed, mathematically fabricated acoustic profile that differs significantly from the environmental baselines the human brain evolved to process. This skewed acoustic profile causes the primary acute complaint among users, a distinct sensation of intense atmospheric pressure building against the tympanic membrane. Empirical measurements utilizing acoustic mannequins prove conclusively that no actual physical pressure change occurs within the ear cup. The sensation stems from an error in predictive coding. The auditory system evolved to rely subconsciously on the constant low-frequency environmental rumble as a baseline indicator of normal atmospheric density and stable barometric pressure. When the digital processor abruptly annihilates that low-frequency baseline, the brain's predictive models fail. The central nervous system falsely interprets the synthetic silence as a massive, hazardous drop in barometric pressure, simulating a rapid high-altitude ascent. In a biological imperative to protect the inner ear, the central nervous system commands sustained, involuntary contractions of the tensor tympani and staccateus muscles. The brain is violently and continuously attempting to manually equalize a pressure gradient that does not physically exist. Because the actual atmospheric pressure remains completely stable, this mechanical popping action fails entirely. The prolonged, futile contractions of the tensor tympani cause rapid muscular cramping. This specific muscle is innervated by the trigeminal nerve, a primary nociceptive pathway for craniofacial pain, meaning the localized cramp translates immediately into a deep, dull, radiating temporal headache. The classic ANC pressure headache is effectively self-inflicted. It is the physical collateral damage of the central nervous system, triggering its own pain pathways to correct an evolutionary math error. The consequences of this mathematical erasure extend into the vestibular labyrinth. The inner ear's otolith organs are highly sensitive to low-frequency acoustic vibrations, relying on this continuous data to cross-reference and stabilize the body's spatial positioning. Activating noise cancellation while walking through a dynamic environment creates a Category B sensory conflict. The visual and proprioceptive systems accurately register physical motion, but the artificially isolated ear registers a completely static, dead acoustic void. The brain is presented with conflicting afferent data. The eyes and body report motion, while the ears report a static, silent vacuum. This contradiction routes distress signals directly to the vestibulocerebellum and the area postrema, inducing cold sweats, severe nausea, and the vascular dilation that drives throbbing migraines. The nervous system reacts to this sensory discrepancy by triggering autonomic distress signals in the vestibulocerebellum. This mechanism mirrors the pathology of simulator adaptation syndrome, where the body's motion sickness protocols activate in response to mismatched spatial data. Beyond acute muscle tension and motion sickness, frequent users face a secondary, chronic neurological mechanism operating within the auditory cortex, based on a dynamic range normalization principle, clinically referred to as central gain. This visualization shows the brain's neuroplastic adaptation to artificial silence. When the external environment is muted, the auditory cortex automatically turns up its central gain. It begins listening with desperate, abnormal intensity in an attempt to maintain situational awareness. The immediate cognitive penalty of this amplification is severe. The hypersensitized brain amplifies the user's internal biological noises, cardiovascular blood flow and respiration, alongside the faint high-frequency hiss of the digital processor, accelerating sensory fatigue. Removing the headphones initiates withdrawal symptoms. The auditory cortex remains temporarily locked in its hypersensitive state, a condition known as hyperacusis. Normal, safe environmental sounds, such as conversational speech or shifting chairs, suddenly register as disproportionately harsh and physically painful. Clinical audiologists are currently debating whether this adaptation goes further, potentially inducing auditory processing disorder. Continuously isolating pristine audio deprives the developing brain of the neurological exercise required to filter speech and maintain spatial segregation in complex, noisy environments. Utilizing profound acoustic isolation to escape daily noise inherently degrades a user's biological sound tolerance threshold, resulting in severe sensory shock and cephalalgia upon returning to the real world. To fully deconstruct the physiological distress, we must differentiate these neurological illusions from the purely extracranial, mechanical damage caused by the headphone engineering constraints. Because digital signal processors struggle to cancel highly transient, high-frequency human speech, audio engineers must block those waves physically. This necessitates relying entirely on passive noise cancellation via dense polyurethane acoustic foams. To achieve this passive isolation, the ear cups must form an impenetrable, airtight pneumatic seal against the skull. This design dictates a continuous inward mechanical pressure, measured in newtons, known as clamping force. This force targets specific anatomical landmarks. Sustained mechanical pressure directly over the temporalis muscle restricts local vascular blood flow, causing rapid ischemia and lactic acid buildup. The result is a classic vice-like tension headache. The gravitational mass of the device compounds this strain. The inclusion of dense lithium-ion batteries and massive copper voice coils significantly increases the device weight, compressing superficial cranial nerves at the vertex and triggering shooting occipital neuralgia. A significant portion of the ANC headache epidemic operates independently of digital algorithms. It is simply the brutal, ischemic reality of strapping heavy, localized industrial clamping vices to a human skull for hours on end. The necessity of this hardware becomes clear when examining its occupational origins. As we see in this image of an aviation professional, Active noise reduction is mandatory in hazardous environments, where extreme noise causes irreversible cochlear destruction. Occupational health authorities establish strict parameters for these environments. The recommended exposure limit is 85 A-weighted decibels, governed by a 3 decibel exchange rate. This means that for every 3 decibel increase in volume, safe exposure time is mathematically halved, making highly effective isolation critical. Yet the Centers for Disease Control simultaneously warns against occupational overprotection. Mathematically erasing too much environmental sound severs situational awareness, actively detaching the worker from their surroundings. Complete acoustic isolation serves as a double-edged sword across all environments. It successfully protects the mechanical structures of the inner ear from destruction, but inherently destabilizes the user's spatial awareness and baseline neurological processing. To combat the physiological fallout, modern engineering integrates structural mitigations. Micro-perforated acoustic relief vents physically break the rigid pneumatic seal to naturally equalize trapped air pressure in the ear canal, mitigating the barometric illusion without destroying low-frequency cancellation. Software mitigations like transparency modes allow a highly controlled fractional bleed of natural ambient noise to reach the tympanic membrane. This continuously feeds the vestibular system the exact spatial acoustic data it needs to prevent sensory conflict and cybersickness. For chronic headache sufferers, clinical audiologists recommend open-ear bone conduction transducers. Because these bypass the ear canal entirely, they completely eliminate the predictive coding barometric error and exert zero inward pressure on the temporomandibular joint. Ultimately, physiological distress requires disciplined behavioral protocols. Professionals must follow the 60-60 rule, maximum of 60% volume for under 60 consecutive minutes. Taking a mandatory 5-minute sensory break provides immediate biological relief. It physically flushes lactic acid from the ischemic temporalis muscles, forces the tensor tympani to release its muscular spasm, and prompts the auditory cortex to downregulate its central gain. Using noise-canceling devices safely requires managing them as active physiological interventions rather than passive conveniences. We can only protect our long-term hearing by respecting the absolute boundaries of our neurovestibular tolerance.